Let's get started with cryptography overview. What exactly is cryptography? It is the science and the study of hiding any text or information so that all in the intended, only the authorized people can read it. What we are mainly concerned with IT security is obscuring information by converting plain text to ciphertext. This is what we mean for the encryption step. Next, the decryption step is converting the ciphertext back to plain text. Well, there will be cryptographic hashing where we can't get plain text back from ciphertext. So, look at the diagram. We have plain text. This is put through the algorithm which is publicly known. To make the encryption unique, we need a key, which can be considered as a password. The result will be the ciphertext, which we should not be able to figure out the key as well as the plain text. Then we will need to use the ciphertext again and pass through the decryption algorithm and the key. The ciphertext as well as the key run through the decryption algorithm and the result is the plain text. In summary, all these steps together is cryptography.
Cryptography brings together lots of interesting aspects. It's got human conflict. You've got the good guys and the bad guys, the people fighting against each other. That makes it interesting. That there's communication involved. So there's all the questions of coding and representing information. There's the questions of algorithms. What are good algorithms for doing this? And the questions of definitions, proofs. How do you prove anything about these systems once you've designed them? So there's lots of human interest, mathematical interest, systems kind of questions, all tangled up together. Now, cryptography, it turns out to be a wonderfully rich source of interesting problems. The requirements for the problems are butting up against each other. That also makes it interesting when you have a problem where it seems like the requirements are just insolvable. But in the end, if you think about the problem the right way, you find a solution, find a way through somehow.
I wasn't involved at all in crypto research. I studied mathematics. I was looking for a place to stay after finishing my PhD, and then I got an invitation from MIT. I got a nice letter from Ron saying that he's happy that I'm going to come to MIT. He informed me for the first time that this is the course that I'm going to teach, and this was on a topic that I knew very little about. So I was totally freaked out, and I immediately went to the library and tried to read as many books about algorithms and complexity theory and all the parts of computer science that I didn't know much about. I think that I even had to look up in a dictionary what cryptography is all about.
Suddenly something happens to somebody who becomes a mathematician, and it's much like falling in love. That's what happened to me. I suddenly, almost on a single day, sort of saw this inner beauty of it all that isn't revealed to most people. Mathematicians understand it. And it was a kind of beauty and pristine world that I've been engaged in ever since. I was interested in a very ancient discipline called number theory. It had been studied for at least 2,000 years, and at various times in its life, it had burned brightly, and at various times it had just been an ember kept alive by a few people. And right when I was becoming a PhD, I happened to be fortunate enough that that field had collided with another field that was emerging called complexity theory, theoretical computer science. But mostly I was interested in doing research to discover new things, to wander around this glorious sort of domain and to peek under rocks and on top of shelves and see if I could spot something that my predecessors maybe overlooked.
RSA steps to creating key. First, we need to select two very large random prime numbers for P and Q. For this example, we select small numbers to make this calculation easier. That is 11 for P, 5 for Q. Next, we need to compute N, which is equal to P times Q, which is 11 times 5 equal to 55. Next step is to calculate the pi n, which is P minus 1 times Q minus 1, which is 11 minus 1 times 5 minus 1 equal to 10 times 4 equals to 40. Thirdly, to select public E. E must be smaller than pi n and is co-prime, which means two numbers that doesn't share any factors except itself and 1. Here's the options: 3, 5, 7, 9, 11, 13, and 17, and so on. For this example, we will be using 7. We have to calculate decryption key. Using 1 modulus pi n, which means d times 7 equal to 1 modulus 40, we will use the Euclidean algorithm to find d. Now, we put 40 at one side of the equation and find out how many times 7 equals to 40. The answer is 5 remaining 5. Now, 7 move to the other side of the equation. With the remainder of 5, how many times of 5 equals to 7? The answer is 1 remaining 2. Now, move 5 to the other side of the equation. With the remainder of 2, how many times of 2 equals to 5? The answer is 2 remaining 1. By using extended Euclidean algorithm, move 1 to the other side of the equation. From the equation above, 5 minus 2 times 2. So now, substitute the 2 from the line, so 1 equals to 5 minus 2 times 7 minus 1 times 5. Extend the equation, makes 1 equals to 5 minus 2 times 7 plus 2 times 5. So combining the equation makes 1 equals to 3 times 5 minus 2 times 7. Now, substitute 5 from the line, makes 1 equal to 3 times 40 minus 5 times 7 minus 2 times 7. Extending the equation, 1 equal to 3 times 40 minus 15 times 7 minus 2 times 7. Combining the common value, 1 equals to 3 times 40 minus 17 times 7. Now we have two original values, which is 14 and 7. The important number is in front of the encryption key 7, which is negative 17. If this is a positive number, it will be our decryption key. But in this case, we calculated d equal to negative 17 modulus 40, so d equals to 23 modulus 40. The result is that receiver knows N and public key E. The sender can use N and E to encrypt the message. The receiver can decrypt the message using D as well as pi n. Thank you for watching. I hope you enjoyed the video.